What the is that? All-moving wingtips, or AMTs. The Chinese seem to be borderline obsessed with this solution that we haven't seen anywhere else. We have seen them on the J-50, but also on the two big drones presented at the V-Day parade in September 2025. And I couldn't, for the life of me, make sense of that solution. Why would you want such a complex, unproven solution, potentially even a heavy one, with all sorts of structural and aeroelastic implications? That's what I was thinking, but there had to be a reason. I had to find an explanation. I couldn't find a book covering the AMTs. None of the book I have, and I have quite a few, even mention them. No, 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 no. So I had to dig deep into some relatively obscure research papers. Some of the papers were Chinese, and I could only get them with the help of the wonderful M7 Discord community. And in the end, of all the papers, there were two that made everything clear. And to make a long story short, the Chinese are right. But to understand why, we need to go on a journey together. And the things that we are discussing today, I am sure you will not find anywhere else on YouTube. Hi, I am Gas, and this is Millennium 7. Understanding why AMTs make sense required quite a lot of research on the internet, even on the Chinese internet. The all-moving wingtips are not a Chinese idea. I was unaware before doing the appropriate due diligence, but the first to conceptualize the AMTs were the Horten brothers for their flying wings. The NACA, the entity that would later turn into NASA, made some studies about AMTs in the 50s. Messerschmitt-Bölkow-Bohm in Germany conducted a wind tunnel test campaign in the 80s in the context of the studies that will later inform the Eurofighter design. They called the AMTs wingerons, but the concept was abandoned nonetheless. Later, in the 90s, there have been military and DARPA-funded studies in the United States, but again, the concept was never developed despite having been judged very promising. To be honest, the whole idea was actually forgotten till we saw it applied on the J-50. The main configuration features of the J-50 are, in fact, the lambda wing, the absence of a tail, and the AMTs. And these three are inextricably connected through an overarching requirement: stealth. As many of you know, stealth is a design feature to reduce the equivalent radar cross-section of an aircraft such that it reflects a small amount of energy towards the radar emitter, reducing the distance at which the detection may happen. Stealth is measured by the radar cross-section, RCS, which is a number expressed in square meters, the smaller the better. RCS is not just a single number associated with the aircraft like you often hear. The RCS varies with the aircraft aspect, so it is better expressed with a spherical diagram centered on the aircraft. I hope it makes sense. Anyway, a complete discussion of stealth is way beyond the scope of this video, but it is enough to know that the lambda wing has several advantages when it comes to stealth. The name of the wing comes from this indentation on the trailing edge, which vaguely reminds the capital Greek letter lambda. The corner is called the turning point of the trailing edge, and the fact that the trailing edge is broken in two reduces the direct reflection of the aircraft, particularly when seen from behind. Furthermore, it is possible to align the two trailing edge segments with other aircraft elements, like the intakes or the chine, something that you can do on a delta wing, for example. A particularly important alignment is the one between the leading edge and the trailing edge of the wing, because this aligns both reflections and diffusions to just a couple of directions. From an aerodynamic point of view, the lambda wing has a better lift-drag ratio at cruise speed than other stealthy wings like the delta wing or rhomboidal wings or the diamond wing. This is because the external part of the wing resembles a normal swept-back wing, which is still the most efficient in cruise. However, if the requirement is stealth, the lambda wing is not enough. Well, it is not enough if you want broadband stealth. In fact, one of the most effective ways of reducing the aircraft RCS is removing the tail. No vertical or horizontal surfaces. And it is easy to understand why. First of all, what is not there cannot reflect the radar waves. Second, the tail creates plenty of corners and relatively complex geometries which are prone to create reflections. Obviously, the tail is there for a reason. It is necessary for the aircraft stability and control. The horizontal tail ensures pitch stability and control. The vertical tail does the same in yaw. And both are problems with the lambda wing. Pitch stability and control in cruise condition is not a particular problem. The wing allows for the aircraft to be stable. In fact, the wing sort of behaves like a hybrid between a delta wing and a swept-back wing, and the delta part maintains the stability through a system of vortices like the delta does. The external part works like a normal airfoil wing, generating lift through the airflow above and below the wing. To maintain stability, the wing must feature a slight pitching down moment, which is usually obtained by using reflex airfoils. Position and structure of the wing vortices depend on the wing form factor, how fat or thin the wing is, and the curvature of the leading edge. But the vortices do exist, and if the center of gravity is ahead of the lift center, the aircraft is stable.
This is not technically correct, sir, and even if it was correct, is too complicated for the average viewer.
Yes, I notice. I'm getting to the point. I know it's a complex subject, but our viewers are intelligent people, and they will follow. And after all, I can't make an entire course about wing design now.
As I mentioned, I don't think that this is very simple, sir.
Otis, you should not be here. You're still recovering.
Considering that my battery is still weak, I returned to the charger. But don't say you weren't warned, sir.
Yes, Otis, you warned me. Everybody's taking note that you warned me.
Sir, did you order the new battery?
Yes, I did. It just takes some time for the delivery.
Yes, because we live in the middle of nowhere.
So what was I saying? Okay, so much for the pitch stability. But what about the lateral stability, the aircraft yaw? Well, the lateral stability is really poor. It is really poor because in a tailless aircraft there is no real mechanism to correct the yaw due to maneuver or gust. Several solutions have been proposed. All of them, though, involve moving some aerodynamic surface differentially. Split ailerons, for example, have a section that moves up, a section that moves down. The sum of the two local lifts cancels, but the drag increases. Another possibility is using spoilers on the wing, which move differentially, cause different drag on each side of the aircraft. They have various names. Sometimes they're called split rudders, but they are spoilers anyway. They are devices that just produce drag. The B2 is a classic example of a lambda wing with both these types of control surfaces. And using these surfaces is exactly the problem, because the lambda wing has a problem: the pitch break. Pitch break is a sudden separation of the flow in the external segment of the wing from the point where the lift vortex separates outwards. It happens quite suddenly when the angle of attack reaches a limit value, which depends on the geometry of the wing, but in practice tends to be relatively small, around 10 degrees or even less. The result is a violent pitching up moment that makes the whole wing stall. The B-2 lost in the incident in February 2008 experienced a pitch break caused by malfunctioning sensors. Now, wings with bad stalling behavior are not exactly news. There have been plenty of aircraft with a similar problem. Well, yes, but in this case, with the Lambda wing, you cannot just twist the wingtip to delay the aileron stall like the vast majority of airplanes do. Or you can, but it is not very useful because the stall is extremely quick and extends almost immediately to the entire external segment of the wing. And that segment is exactly where your control surfaces are located. You may have additional control surfaces inwards, but your most effective ones, the ones that you need to get out of a spin, are located exactly there. With a turbulent detached flow, they completely lose effectiveness and the aircraft stalls and it is very difficult to recover. For an aircraft like the B-2 or a stealth drone that doesn't maneuver much, this wing bad behavior is not a terrible problem. Modern control laws can make sure that the critical angle of attack is in practice never reached. But for a fighter, the Lambda wing should be clearly a no-go. Increasing the angle of attack is necessary to make sharp turns, carry asymmetric loads, but also to resist to gusts, particularly when flying at low altitude. If the stall happens at low angle of attack, and it is so bad, it is not a behavior suitable for a fighter. A fighter with a Lambda wing and without a tail would need a way to delay the stall and to recover from it. So, for a fighter, the Lambda wing is practically unusable. Right? Okay, but what if I am really stubborn and I want to make use of the stealth features of the Lambda wing on a tailless fighter anyway? In this video, we don't cover the ways of delaying or mitigating the pitch break. They will involve some additional vortices systems, which may or may not compromise stealth, but this is out of the scope. Now we focus on lateral stability and stall recovery. Well, one possibility is using 3D thrust vectoring, which is good, but it tends to be less effective at transonic and supersonic speed. At those speeds, aerodynamic surfaces are overall more efficient. So we would really need an aerodynamic surface that could generate drag and would not be affected by the pitch break. And so it happens that such surfaces do exist, and they are the all-moving wingtips. So the first thing to understand is that the AMTs are not a sort of a cool aileron. Their purpose is not so much to generate lift, but to increase drag. In fact, they do not rotate up and down, they only rotate up, increasing the local angle of attack. Sure, rotating upwards, they increase the local lift as well, and they do generate a rolling moment, but they can be designed with an aerofoil such to minimize this effect, and the rolling moment can be compensated by other aerodynamic surfaces. Actually, you can probably let them stall and they will produce even less rolling moment. On the flip side though, they also increase drag at the wingtip, creating a yawing moment that allows for the lateral control and stability. Sure, you need a digital fly-by-wire system with appropriate control laws, but it really seems that the Chinese did figure it out. Being at the tip of the wing, they don't need to be big to be effective, and if the axis of the hinge is skewed backwards, the lift decreases and the drag increases, making them even more efficient. And crucially, the wing can be designed to lift them out of the pitch brake area, maintaining effectiveness even when the pitch brake happens. In fact, the American wind tunnel tests in the 90s actually suggested that they are very effective to recover from stall exactly because the stalled area does not reach them. Watching the J50, I was very perplexed seeing that in a turn, the inner AMT was tilted as to act against the turn. I was also surprised that they moved a lot and with high angles of attack. But that is exactly how it is supposed to be. The inner AMT was probably just contrasting the inverse yaw in the turn. I was also concerned that adding the actuators at the tip of the wing was adding weight and complexity. But in reality, if the hinge is correctly positioned, the torque needed to actuate the AMTs is even lower than the torque needed for split ailerons or spoilers, making the actuators smaller and lighter. The Chinese designs still have plenty of aerodynamic surfaces with big actuators, most likely for caution, but I suspect that they might end up removing some of them. So, there you have it. If you want a fighter with broadband stealth, you want to remove the tail and use a lambda wing. But the lambda wing is really poor for very maneuverable aircraft, particularly when it comes to lateral stability and stall characteristics. The all-moving wingtips are not ailerons, they don't do anything for the stall characteristics, but they are a very efficient device to increase the drag on the wingtip to guarantee stability and control around the yaw axis. Furthermore, they are very effective for stall recovery. So at this point I'm just wondering, what would happen on the internet if, when the F-47 will be presented to the public, it turns out to feature AMTs? Thank you very much for getting this far into this video. I know it wasn't easy. This video required a lot of research. It required reading a lot of scientific papers, which made me feel young again. And if you liked what you have seen, please consider supporting the video on Patreon by being a member or by any of the other means available. Plenty of people have already done this, and they are absolutely essential to keep the show running. And if you can support the channel financially, please consider subscribing if you haven't, but also interacting with the video, leaving a comment, hitting like, even because with the current algorithm, this is the best way to ensure that you will be notified when another video drops. So this is it. Thank you very, very much for watching, and see you next time.